Good morning, everyone. My name is Sang Shin, and I would like to share my company's experiences on visualizing the spatio-temporal data using CesiumJS. Actually, everybody in this room knows that Cesium is quite great at rendering and displaying the 3D object. But when it comes to the spatio-temporal data, like wind or water, it's a little bit challenging. So I will share our experiences. So how to visualize the spatio-temporal data using CesiumJS? Actually, my company is, over the couple of years, my company is involved in several projects focusing on the visualizing the spatio-temporal data. And we have developed our own JavaScript called Mago3D.js. But nowadays, we moved from Mago3D.js to CesiumJS to join a broader ecosystems. So from now on, I would like to share 3 cases. The first one is sponsored by the Korea Meteorological Administrations. So we have successfully developed for the 3D visualization system for the KMA. So our first case study focused on the visualizing the numerical data produced by KMA or other national weather agencies like NOAA or KMA or other areas. So I'll show you the 3 cases visualizing the ISO value surface of the weather variables. And the second one is visualizing the streamline data like wind flows. And the last one will be the visualizing the slice plots of 3D volumes. First, we have to pre-process the data produced by KMA or ECMWF or NOAA. And then so actually, our system will ingest the ECMWF data or KIM data or whatever data, and we have to convert those data to a unified grid format like longitude, latitude, altitude, and the values, and then we can visualize the many things. So we use ISO surface to represent areas of constant values. This is very effective for visualizing volumetric data like temperatures and the pressures or cloud density. So at first, we take grip2 data or NetCDF data and convert those data to a GLTF format using matching cube algorithms. And then we change the coordinate systems from grip2 to vertex position 2 and the also centered and also flat coordinate systems. And then this is a streamline visualization inspired by a Cesium team, but this is not 2-dimensional, but 3-dimensional. And we took the data from KMA, and we converted those data to CesiumJS friendly data. And then finally, we visualized those wind flow data like this. And then this is how we implemented those kind of streamline visualization, calculated the particle positions, and then render the trail mesh. And the slice plot. Actually, slice plot allows us to render 2D cross-section of the 3D data. This is very useful for forecasters for analyzing the data at a specific altitude and the plane. So slice plots also can help to visualize 3D grid data like this. Also, we can render a mesh with 3 generated planes, x-axis and y-axis and z-axis like this. So since last month, this system is in official use in KMA among the forecasters in Korea. So right side now, you can see the real systems used by our forecasters in KMA. So now they can take numerical data and then they can upload those data from their supercomputers and other things, and they can visualize many numerical data, including wind, temperature, and pressures, and other things using CesiumJS. Another case is a chemical dispersion case. So actually now you can see how the chemical materials are dispersed over the time and over the surfaces. So this project is for the Ministry of Environment in Korea. So the first one we have to do for the visualization is that the data convert, and we have to reduce the file size. And then we have to interpolate the data, and then we can implement a volume rendering like this. There is a huge problem in this project because usually simulation data is extremely very large, over 30 gigabytes. Sometimes it is exceed more than the 300 gigabytes, and this is too big to transfer and to render in web browsers. So we have two solutions. The first one is we have to reduce the data using a data encoding. So left side, you can see how we reduce the data from raw data to PNG encoded data. And the second solution is how we rendered those data. So instead of sending every single time step, we just send just the keyframes, and the client side, the CesiumJS, will interpolate in terms of the g-axis and in terms of the time series. And then also we have applied the volume rendering for the realistic visualizations. We inspired by this from MRI and CT. So, and this is the real result. And so at the first year, we implemented like this. It's a daily simulation data. So every day, how the toxic gas release was dispersed like this. And the second year, we applied this technology to the real city called Dangjin. Actually, there are many chemical plants in Dangjin city, and many citizens are quite worried about the chemical accident. So using this system, we can simulate with the wind direction, wind speed, and the humidity, and the temperatures, and then the released toxic types. And then together with our chemical expert, we can simulate it like this, and then we can determine how many people will be exposed to this kind of chemical accidents, and how much those will be exposed to our citizens. And this year, we are developing new types of this chemical dispersion using a magic cube algorithm developed for the KMA like this. And the last one is the fluid simulation and visualization. So we explored two approaches. The first one is real-time simulation and pre-computed simulation. So this means that we would like to visualize the water flow and the flood and other things in your web browsers. So the left side is real-time simulation. So real-time simulation allows for the live interactions, but can be very slow. But because our web browser calculates many things in a client side, so also it requires a powerful client. And the pre-computed is already, we can pre-compute the simulation data, and then we can take the data from the server, and we can render the data using a CesiumJS. So we have two types of simulation and visualization. So actually, left side now you can see the real-time simulation of the water flows, and the right side you can see the pre-computed visualization of the flood. So this is a comparison chart between real-time and the pre-computed simulation. Left side now you can see if you use the real-time simulation, you can interact lively. But in a pre-computed simulation, you could not. But also in a real-time simulation, all the things will be calculated in your web browser. So we would not need any network traffic. But if there is a pre-compulated simulation at the server side, we should take that from the server. So we have to have a huge network traffic. Also, real-time rendering will be very slow because it will calculate many things in web browsers. But pre-computed simulation, rendering speed will be fast. Also, in terms of the memory use, real-time simulation is very low, but in terms of pre-computed simulation, the memory use will be high because we have to take the current simulation data and then the before and after data. Also, time flow is just one way, while pre-computed area is two-way. So actually, there are several methods for visualizing the fluids. So we explored actually three types of the fluid visualization. The first one is grid-based, such as a height field or height map method. Also, we explored the particle-based. just like middle one. Also, we have explored the volume-based, like last one. And then we have chosen the first one. We choose the height field method for its performance, and also it works by taking a simple 2D grid mesh and displacing its vertex up or down based on the color values in a water height texture. And this is very, very efficient. So we use this height field visualization method for the fluid dynamics. So also we have been inspired by the very well-known WebGL demos, Evan Wallace's WebGL Water. So we have used this kind of algorithm to the real terrain. So this is a result of the visualization of implemented simulation as a wireframe. Also, in terms of the water flow simulation, we developed lattice-based simulation using shallow water equations, which can be discretized into 2D lattice with the equations derived from the Navier-Stokes equations, enabling calculating using GPUs, and then it's very, very suitable for the large-scale terrain-based water flows, such as floods. Also, other computational fluid dynamics programs would have been very similar, but would have had different policies for calibrating the simulation, and such as handling boundary conditions and other things. So here is a comparison chart. So in short, shallow water equations are suitable for the very small areas, and then suitable for the shallow water, tsunamis, flood modelings, and the ocean tides and the river flows. That's why we use the SWE. And then so now you can see the real simulation data here. So now you can see the water flow down to the area here. Also now you can see the dam here. And it blocks the water flow. And then if we destroyed the dam, and then the old reservoir of water will flow down to the valley. So we accumulate the water. And then the left side panel, we can adjust the other things. And then we can destroy the dam here. Come on. Yes. Now we destroy the dam, and then accumulate the water flow down to the valley. So this is a real-time simulation. In your web browser using CesiumJS. Thank you. And if you have any questions? Yeah.
Yes, I had a question concerning the WebGS that you guys integrated into your real-time simulation. Mm-hmm. So you said you guys had like some problems with the real-time one, and did you guys like find any solution, another maybe technology, maybe like incorporating native or anything else?
Real-time.
Yeah. You said that the real-time part like had some issue because of like the amount of data that was processing. Yeah. So I wanted to know if
that's a great question. Actually, we have developed, just like I mentioned, we have developed our own real-time simulation model like this. Actually, my guys out there in Korea, he read many papers, and then he implemented the shallow water equations in a JavaScript, and then he applied that. But the problem is that, as you see here, the area is a little bit smaller. So if you would like to extend that area, you have to change the resolution of the cube. For example, this is just a 1 meter by 1 meter cube. But if you increase the size of the cube to 10 meter by 10 meter, and then you can have the more larger area for your simulations. Yeah. Any other questions? Okay, thank you.